In this video we're going to talk about these two theorems that give us some properties about connected spaces. The first one is that given a connected space, if we have some set that is in the middle between A and its closure, then that set must be connected. And the second one is that the image of connected spaces under continuous mappings are also connected. These two theorems might seem meaningless now, but they're actually very useful, and we will use them a lot in the exercises, and the techniques that we use to prove them will be very useful for us in the exercises and later on for more important theorems. So let's start with the first one. We have that A is connected and this inclusion. Let's make a drawing to see the situation. We have here our space, our set A, then there's B, and finally we have here the closure of A. So to prove the theorem, we will suppose that B is not connected and try and reach a contradiction. So let's suppose that B is the union of two sets, let's call them U and B, where U and B are open, their intersection is empty. So basically, if this is our set B, we are saying that we can separate it with one set U and another set B. But now A is connected, so A cannot be separated. That means that A must be on only one of these sets. It can be U or B. Obviously it's the same in this situation because it's abstract. So because A is connected, then A is a subset of U. And from this, because of the monotonicity that we know that the closure satisfies, we solved an exercise on that before, we know that A closure is a subset of the closure of U. But if U and B are a separation of B, then it must be the intersection of B with the closure of U empty. So this is telling us that the closure of A is here. It's also not touching B. So this leaves no other option than for B to also be here. And then B has to be connected. So then we will have that B has to be the empty set. And so there was no separation in the first place. And this is exactly what we had to prove. Now let's continue with the second theorem. This theorem says that continuous functions map connected sets onto connected sets. So for this, let's suppose we have f, a function that goes from x onto, and here I could say y, but we want this function to be surjective because we want to see if the image of x is connected. So let me abuse a bit my notation here and say that this function goes from x to f of x, because this is the set that we want to prove is connected. This is our function and x connected. Like we did in the last theorem, we're going to suppose that f of x can be separated into the union of two sets, where U and B are open and their intersection is empty. Now remember that this function is continuous, so that means that the preimage of open sets is open. In particular, the images of U and B. But now, because the function f is surjective, these two sets form a separation of x. So x can be written as this. Obviously, these two sets, their intersection is empty because f is a well-defined function, and so we have that x can be separated, so x is not connected. But this contradicts the hypothesis that x was connected. And then what must happen is that f of x is connected. And with this, we finished this video.